This is the second video on how to draw Lewis structures from a molecular formula. So we're going to go ahead and do that, and along with that, determine the shape and polarity for N2O3. Now remember, to start, you always want to make sure you know the number of valence electrons that you're dealing with for this particular formula. So nitrogen has 5 electrons, but there's 2 of them, so we'll say 5 times 2. And again, you can do this at any time during the building process, but we'll do it at the beginning here. Oxygen, there's 3 of them. There's 6 electrons each. It's in that 6th column, 6A, in the main group element. So we can say 3 times 6, which is 18. So I'll just go ahead and put 18 here. So 18 plus that 10, that's going to be our 28 electrons. 28 electrons have to go in to whatever we build. Now the middle is always going to be our nitrogen, but we have 2 of them, so we're going to do the same thing we did on the last video. We'll put those 2 nitrogens and say everything's going to go around those 2 nitrogens. So we put that in the middle, and we start just going around the outside. It doesn't matter. I could have gone down here with the other additional oxygen. But that's as good a frame as you might propose for N2O3. Now, if we look at this frame, the frame has electrons already in it of those 28 we need. So 2, 4, 6, 8 electrons in the bonds, because each bond represents 2 electrons. So we can really say this is now 20 more electrons have to go in. We put them from the outside in. So we're not going to put the dots on the nitrogen. We're going to put them in on the oxygens. I'm going to go a little bit to the north here, just to, if I have to drop down, I'll have some space down here to do that. So let's put those electrons in, those 20. 2, 4, 6, 8, 10, 12, 14, 16, 18. Now I'm going to go ahead and put the last 2 on this nitrogen, because of the 2 nitrogens, this one has 3 bonds off of it right now, and this one only has 2. So I put that last 2 dots on this nitrogen, those last of the 20. Let's count them up just to make sure we have 28. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 23, 24, 26, 28. So yes, we have all of them added in, the lone pairs. But now we need to drop down, I believe, twice. And here's why. We can look at the nitrogen here, and he has only 2, 4, 6 electrons around him. So there's nothing to drop down here. So there's no choice here. We're going to drop from the oxygen 2 of these dots, or a lone pair, so we get that double bond. But if I look on the other side here, I'm going to just draw this a little bit down so I have some space. The other side, this nitrogen also has only 6 electrons around it. Now this is a choice. Now again, this would be where you have resonance. I can say I can drop from the north or from here. I would actually consider both as the final picture of this structure. I would say I have 2 resonance forms. But we'll draw it from the north here. It came down. But again, I could have also considered from the south. It could have come up. And now we can look at charge. We've dropped down. Everybody's happy. 2, 4, 6, 8. 2, 4, 6, 8 as far as the number of electrons around it. But we need to still show charge. Now charge is going to be different for these 2 nitrogens. I can see that by the Daniel-Gonzalez rule, which we said kind of looks at the number of bonds off of N and O. This oxygen's happy. He has 2, 4, 6, 8 electrons around him, and he has 2 bonds off of him, so no charge on this oxygen. This nitrogen is also happy. It has 3 bonds off of it and 8 electrons around it. But this one, we notice, has 1, 2, 3, 4 bonds around it, so he has a positive charge. Now looking at this formula, I saw that there was no charge shown on it overall, so there has to be a counter charge, a negative charge somewhere. And we have that right here. This oxygen has only 1 bond off of it, 1 less than what it wants. 1 less, kind of thinking deficiency, but really it's an excess. we can say it has a negative charge. So now we've added in the lone pairs, we dropped down, and we've shown our charge. We've done all the things we need to do to satisfy what's asked of us for this box. Now this is then our final Lewis structure, but remember, this negative charge is really split between these two oxygens. So it'd be like saying I have half of the negative charge here and half the negative charge here. All right, so that's great. Let's look at geometry. Around these two nitrogens, it's actually the same geometry as far as around the nitrogens. So we'll draw our final structure, clean it up a little bit. But let's look at the geometry around this nitrogen. It has a lone pair, so that's going to count as, remember, you need to know lone pairs, and you need to know the number of atoms. It has one lone pair, but it has this atom off of it and this atom off of it. So we would say around this nitrogen it's trigonal planar. Around this nitrogen we would say, oh, it has no lone pair, but it has 1, 2, 3 atoms off of it. So both are trigonal planar. So let's just draw that in, and we are almost done. We're going to consider now also the overall polarity, but let's get this finished first, and I'm trying to draw a trigonal planar as best I can. And again, we could have had this oxygen up here with the negative charge. We're just showing the one on the south side. You do need to show charge, so I'm going to go ahead and put that back in. The final Lewis structure looks like this. You have to show formal charge if it has it. Now you don't have to show bond polarity, but we can consider that and just use arrows for that. This nitrogen is not as electronegative as this oxygen, so there would be a little bit of a slight pull of electrons in this bond out towards the oxygen. And we have an overall polarity already before we even consider bond polarity. We have charges, so and this would be equal, but they wouldn't be canceling because they're going off not in 180-degree angles to each other, but they're going off in 120-degree angles to each other. But we can kind of say this would have polarity for this reason. I consider all these bond polarities, and whatever I have over here isn't matched by what we have over here, like we saw with N2O4. So this would have, yes, an overall dipole moment. It's probably going to have some arrow as an overall polarity on this side because we have such an extreme amount of charge over on the right side. But either way, this would be more soluble in water than that last structure we saw, which was N2O4. It was, I guess, it was not polar overall. Now this one did have more charge though, so that actually can cause some, I guess, tendencies to move away from that trend of if you have a dipole moment, then you're more likely to be soluble in water. Because this one did have more charge. It had 2 positives and 2 negatives. This one has just kind of just one of each. This one spread them out. This one is spread about 2 different oxygens. But this one did have overall more charge. But that's how you do the game. That's how we go from the molecular formula all the way to the Lewis structure and considering polarity. This is a great problem. Thanks. Bye-bye.